Hi everyone, this is Prof. K speaking, and this is going to be the integrated rate law video, part 2. So in this video, we're going to perform the integrated rate law calculations for a first and second order reaction and see how we can identify the order of reaction from concentrated and time data using the integrated rate law. So this is just a review of what was at the beginning of the last slide, but for zeroth order, first order, and second order reactions that depend on K, we can also write instantaneous rates where we connect how quickly A is disappearing or being consumed as a function of concentration, because it's related to the rate and the way that this reaction is proceeding. And the difference between a first order and a second order reaction is this exponent here. So when we have to integrate this expression, they're going to take different forms because they have different dependencies on concentration. So now we're going to integrate the instantaneous rate for a first order reaction. So before we take the integral of this, I like to rearrange it so that my variables are separated so that it's easier to do the integration. So I move the concentration of A over to be under the change in A, and I multiply dt to the other side to get kdt. And in this particular problem, I also move this negative sign just because it looks a little neater in the math, but you could solve it with the negative sign on either side. And so then we take the definite integral from 0 to some time for our particular reaction so that we can determine the function of A as time changes. And so when we integrate both sides, it helps to recognize that if you have the derivative of something over itself, that's probably a natural log. And so this integrates to the natural log of A is equal to negative kt, because if you integrate dt, you get time. And so then we want to evaluate that over the definite integral of 0 to t. So we have to plug in t and 0 to both sides of this expression. And we get that the natural log of the concentration of A at some time minus the natural log of the initial concentration of A is equal to negative kt. And then I didn't write it here because it's not really interesting. This would be plus k times 0, but that turns into 0 and it goes away. So if we have natural logs, this subtraction here, you could identify this as one form of the integrated rate law, but we can also rearrange this to look slightly differently if we want to have the concentration of A by itself as a function of time. So if you have a subtraction of natural logs, then you can do the division of those natural logs. And then to get rid of a natural log so that AT is by itself, we can take this whole function to the exponential power to get rid of the natural log. And we're left with the concentration of A at some time over the initial concentration is equal to e to the negative kt. And if we want to get the concentration at some time by itself, then we just multiply both sides by the initial concentration and we're left with this expression. So from the instantaneous rate of minus dA dt equals Ka, so how quickly we use up A as a function of A, we can derive two forms of the integrated rate law. One, where we leave the concentration as a function of time inside the natural log, which is occasionally useful, and I'll show you an example of where this is useful in a minute. Or if we want to directly calculate the concentration of A, we can do that as a function of time using this exponential term. And so these are two valid forms of the integrated rate law for a first order reaction. So if we're faced with data that maps out this concentration of A as a function of t with respect to time, you'll notice that this looks like exponential decay, or maybe now you recognize that it looks like some sort of exponential decay. And so we can't do what we did in the previous problem, where for the concentration of A, we can't use this slope to as easily identify what our rate constant is. However, if we use this first expression here, we do have something that can be a line if you plot the natural log of A as a function of time, where we have the form that is the natural log of AT is y, and negative k is going to be our slope, and b is the natural log of A naught. So if you're given concentration data and you plot it as the natural log of that concentration data and you get a line, that means that you have a first order reaction and that the slope is going to be equal to the negative rate constant. So having the integrated rate law lets us use this data to identify important physical constants. And so if you have something that looks like an exponent, it might be the case that if you take the natural log of it and you get a line, that you're dealing with a first order reaction. So you'll practice doing these calculations in class, and you'll practice plugging in different times and seeing what your concentration is, or plugging in a goal concentration and solving for time. And so in different contexts, you might want to use different forms of this expression, and it's probably good if you can move back and forth between them. To continue, we're also going to calculate an integrated rate law, going the wrong way, an integrated rate law for a second order reaction. And so in this particular reaction, we have negative dA dt is equal to k times the concentration of A squared. And so once again, the first thing I want to do with an integral is separate the variables so that I can integrate this nicely. And then I take the definite integral of this whole expression from 0 to some time. And I wrote this a as a to the negative 2 because I find it easier to see how to do the integral. So if you integrate something with an exponent, then you add 1 to the exponent and then divide that by whatever the new number is. So here it would be you add 1 to this, you get negative 1, and so then you divide this by a negative 1. And so on that side of the expression, we'll have a to the negative 1, and then it would have been negative, except that we have a negative on the side that we canceled out. So now we have a to the negative 1 equals k to the t. And this integrates the same way as before. dt turns into t. And then we have to evaluate it over our limits of from t to 0. So when we do this, we get 1 over at, which is the same as at to the negative 1, minus 1 over the initial concentration is going to equal kt minus the invisible k times 0, like always. And so the integrated rate law could be in this form, or if we want to arrange it, it could look like this. And so this expression is sort of the neatest way that we can write a second order integrated rate law. So from this instantaneous rate, we're able to derive this expression. And you might question why we had to use a natural log for the last one, whereas here we can do this sort of exponent integral. And that's because in the last problem, we had a to the negative 1. So when you try to divide it by 0, which is the exponent you'd get here, you're dividing a number by 0. And so it doesn't work out to solve the problem like this. And you have to recognize that dA over A concentration is going to be the natural log of A. But we can do the exponential here. And if we change this to a third order reaction where you have dA dt is equal to Ka squared, then down here it would be a to the negative 2 divided by 2. And so this allows us to do higher order integrals as well. But we're going to just focus on the second order integral because it's interesting and it's data that we can practice plotting. So if you just plotted the concentration of A as a function of time for a second order reaction, you get something that declines even more sharply than our exponential equation did for the same initial concentration and rate constant. And that's because in this system, you have a different expression for A's dependence on time. So if we want to generate a plot that has a linear relationship between something in order to calculate some rate constants from data, Instead, we have to plot 1 over a. And if you plot 1 over a, you get this line as a function of time where you can write it in the form of y equals mx plus b, where y equals 1 over the concentration as a function of time, m equals the rate constant, and b equals 1 over the initial concentration. And so we're not going to ask you to do these integrals yourself, but we want you to understand where they came from and to be able to see what you might need to plot in order to derive a rate constant and how you would expect the plots of each type of reaction to look based on the integrated rate laws. And so we'll be using these integrated rate laws a lot, and you'll be asked to recognize what the plots look like. And now you know how they were derived, so that if you ever, either in this course or in future courses, face other rate laws that have different forms, you know the process by which they were derived.